Hi. The first topic in the chemistry syllabus for common university entrance test is solid state. Some of you may not have studied solid state in class 12, but you need not worry. I am uploading video classes on the prescribed topics in 3 parts, which include a lot of previous year multiple choice questions and other model questions for CUET UG. By the way, I am Dr. Suryak Matthew, a retired professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes on topics in chemistry related to NEET, JEE Main and Advanced, CUET, and other similar examinations. If you like the video, please subscribe my channel and forward to others. Let us see how to locate tetrahedral and octahedral voids. When we place a second layer over the 2D hexagonal close packed layer, two types of voids are created. These are the tetrahedral void and the octahedral void. So three spheres of one layer and that form a triangular void, and if the spheres of the second layer fit into the triangular void, this generates a tetrahedral void. So this one is a tetrahedral void. Now another type, that is three spheres of one layer, it forms a triangular void. Now the second layer spheres, so again we are considering three spheres, and this also form a triangular void. But these two triangles are in a staggered manner. When they come close together, this gives rise to an octahedral void. So the red triangle and the bottom green triangle. We know the number of octahedral voids present in a lattice is equal to the close packed structures, and the number of tetrahedral voids present is twice this number. If we consider a unit cell, we must take the effective number of atoms in the unit cell. First, let us see how to locate tetrahedral voids in a cubic close packed structure. Imagine a cubic close packed structure which is same as face-centered lattice. Let me divide this unit cell into 8 small cubes, and I am taking one such cube out, and in these cubes alternate corners possess atoms, and if you join the atoms you will get a tetrahedron, and this consists of a corner atom and the other three are face-centered atoms. When joined, they form a regular tetrahedron. Therefore, one tetrahedral void in each small cube. This one. There are 8 such cubes, so therefore there will be 8 tetrahedral voids. For CCP or FCC lattice, the effective number of atoms is 4. Therefore, the number of tetrahedral voids is twice the effective number, that is 8. For a tetrahedral void, the R void by R sphere. R void means the radius of an atom that can be placed inside this void. And R sphere is the radius of the spheres that make the tetrahedral void. And R void by R sphere is equal to 0.225. And this is another tetrahedral void, and these tetrahedral voids orient along the body diagonal. Here also we can imagine a body diagonal. The tetrahedral voids orient along the body diagonal, 2 tetrahedral voids on each body diagonal. The tetrahedral void are at 1/4 distance. So if you take the center of the tetrahedral void, this is the center, here also it is the center, and that is 1/4 distance from the corner atom. There are 4 body diagonals, and thus there are 8 tetrahedral voids. Let us study more about the structure of diamond. Diamond is one of the hardest substance. The hardness is attributed to its structure. The carbon atoms form a face-centered cubic lattice. Thus, effective number of atoms is 4. In addition, alternate tetrahedraloids are also occupied by carbon atoms. There are 4 body diagonal, and alternate tetrahedraloids means total tetrahedraloids are 8. So therefore 4 out of 8 tetrahedraloids are occupied by carbon atoms. So therefore altogether there will be 8 carbon atoms in the unit cell. So this red carbon atom is a carbon atom on the body diagonal. So it is attached to 4 other carbon atoms in a tetrahedral manner. And this is the body diagonal. Each body diagonal contains 1 carbon atom. Here there is 1, 2, 3 and 4. Altogether there are 8 carbon atoms in a unit cell of diamond. Now let us consider how to locate the octahedraloids. For that again consider a face-centered cubic lattice, CCP structure. And consider this figure. It forms an octahedron. And let me take this octahedron out. That is 1 octahedral void at the body center. This is the center of the octahedron, and this is the location of the octahedral void. And this octahedral void is half the distance of the body diagonal. So this shows the octahedral void which is at the center of the crystal lattice. So in a face-centered cube there are effective number of atoms is 4. Therefore the number of octahedraloids also should be 4. Now imagine this figure. Suppose I combine it with the unit cell, and we can imagine another octahedraloid at this place. That is 1 octahedraloid be present at the center of each edge. There are 12 edges, and at the edges there are 12 octahedraloids. And 1 octahedraloid is shared by 4 unit cells. 1 in here, 2 the other side. So therefore 4 unit cells share this octahedraloid. So this unit cell get only 1/4 of the octahedraloid. So effective number of voids for the unit cell from edge will be 12 into 1/4, that is equal to 3. Therefore the total number of octahedral voids in the unit cell is equal to 1 from the body center plus 3 from the edge center. And that is same as the effective number of atoms in the unit cell. For an octahedral void, the ratio R void by R sphere. R void means the radius of the sphere that could be accommodated within this octahedral void. R sphere is the radius of the sphere that makes the octahedral void. This ratio will be R void by R sphere is equal to 0.414. And octahedral void is larger than tetrahedral void. Let us examine the structure of sodium chloride. In sodium chloride, sodium ions occupy octahedral voids in a face-centered cubic lattice of chloride ions. Sodium ions also form FCC lattice, and both interpenetrate. Each sodium ion is surrounded octahedrali by 6 chloride ions, and each chloride ion is octahedrali surrounded by 6 sodium plus ions. These are chloride ions, and the star represents sodium ions. Both chloride ion form a face-centered cubic lattice, and the sodium ion also forms a face-centered cubic lattice, and both interpenetrate halfway. Packing efficiency in 3 dimensions. First, we will consider the packing efficiency in cubic close-packed structure. In whatever way the constituent particles, atoms, molecules, or ions are packed, there will always be some free space in the form of voids. Packing efficiency is the percentage of total space filled by particles. We will now calculate the packing efficiency in different structures. First, let us consider the cubic close-packed structure. And let this be an atom from the first layer. And now we consider 1, 2, 3, 4, 5, 6 atoms from the second layer. And again 6 atoms from the third layer. And 1 atom from the fourth layer. So this will form ABC pattern, and it is same as face-centered cubic lattice. So this will be the face-centered atoms, and these are the corner atoms. So A, B and C, this is the edge length of the unit cell. So this distance will be a radius. This also will be another radius, and this distance BC consists of 4 radii. And we take BC, that is the face diagonal, as B. In triangle ABC, AB is equal to AC. A is the unit cell edge length, and BC, that is B, is the face diagonal. Now we take R as the radius of the sphere, and now B is equal to 4R. Since this is a right angle triangle, we can write BC square is equal to AB square plus AC square, or B square is equal to A square plus A square, that is 2A square, or B is equal to root 2A. Now B is equal to 4R, or 4R is equal to root 2A, or R is equal to root 2A by 4, or A by 2 root 2. So in a face-centered cubic lattice or in CCP structure, the relation between radius of the sphere and edge length of the unit cell is R equals A by 2 root 2, or A is equal to 2 root 2R. For a face-centered cubic lattice, the effective number of spheres is 4. Therefore, the total volume will be 4 into 4 by 3 pi r cube. Therefore, the volume of the cube is a cube, and A is equal to 2 root 2R, that is 2 root 2R the whole cube. Packing efficiency is the ratio between volume occupied by 4 spheres in unit cell divided by total volume of the unit cell into 100. Total volume occupied by 4 spheres is 4 into 4 by 3 pi r cube. Total volume of the unit cell is 2 root 2 r the whole cube into 100, and this comes out to be 74%. So the packing efficiency in FCC, lattice or CCP structure, cubic close packed structure, is 74%, which is the highest. Now let us examine the packing efficiency in HCP structure. It is non-cubical, and this is the hexagonal close packed structure. Layer A, layer B, and A repeats. So this is the atom in the A layer, center of the A layer, and it is shared by 2 unit cell, that is unit cell above this. So the contribution to this unit cell from this atom is half. Now take the corner atoms, and these corner atoms are shared by 6 unit cell. 3 here, 3 above, and so 6 unit cells share it. So 1 by 6 into 6, there are 6 corner atoms. So the effective number is 1. These 3 are within the unit cell, that is the B layer. So that is totally inside the unit cell, so the effective number is 3. So the bottom layer also the same is applicable, that is half of the central atom and 1/6 from the corner atom. There are 6 corner atoms. So the effective number of atoms in HCP structure, and that is equal to 6. And this is the actual portion of the HCP structure, which is imaginary. And here actually the HCP structure consists of 3 unit cells. And these parts are 1/6 part, and this is the half part, and these are the 3 unit cell 1, 2, 3. Now the HCP structure can be written like this, and the height of the HCP structure BH, and this is equal to 2r. So this distance is, that is the side of the unit cell, that is 2 radii. Now the volume of this HCP structure is equal to base area into height, and the base area is divided into 6 equilateral triangles. So therefore the base area is area of an equilateral triangle into 6. Area of an equilateral triangle is root 3 by 4a, where a is the side of the triangle. And here a is equal to 2r, that is root 3 by 4a square, that is root 3 by 4 into 2r square. There are 6 such equilateral triangles, so total area will be root 3 by 4 into 2r the whole square into 6. Therefore the volume of HCP structure is equal to root 3 by 4 into 2r the whole square into 6 into height, that is h, base area into height. And from trigonometric calculations we can show that the height is equal to 4r into square root of 2 by 3. So the effective number of atoms in HCP structure is 6. Therefore volume of 6 spheres is 4 by 3 pi r cube into 6. Therefore the packing efficiency is total volume of spheres by total volume of HCP structure into 100. That is 4 by 3 pi r cube into 6 divided by total volume of the hexagonal structure into 100, that also is 74%. So both HCP structure and CCP structure are 74% efficient. The vacant space is only 26%. Now the packing efficiency in BCC. Another type of close packing is body-centered cubic close packing. Atoms in body diagonal touches each other. For the ease of explanation, the structure is drawn in an expanded manner. And this blue atom is the central atom, and this one, and these white spheres are the corner atoms. Now we connect. So this is the cube, and atoms along the body diagonal, this corner to this corner, and these 3 atoms touch each other, and let this distance be y. Now we take, or we draw a triangle. The side is x, this is y, and this one is a, and this also is a right angle triangle. Then another triangle here, that is we label the ends a, b, c, d. First consider the triangle BCD, that is a right angle triangle, and here the sides are x, a and a. So x square is equal to a square plus a square, that is 2a square, or x is equal to root 2a. In triangle ABC, now we got this x, a and y. Now that also is a right angle triangle, so y square is equal to x square plus a square, that is root 2a square plus a square, that is 3a square. So therefore y is equal to root 3a. That is the body diagonal in the face-centered cubic structure is root 3a. The length of the body diagonal is AB, and that can be considered as consisting of 4 radii. 1, 2, 3 and 4. So therefore y is equal to root 3a, or root 3a is equal to 4r. Therefore r is equal to root 3a by 4. That is the relation between radius of the sphere and the edge length of the unit cell. And from this a is equal to 4r by root 3. In BCC structure, the effective number of atoms is 2. So therefore the volume of two spheres is 4 by 3 pi r cube into 2. And the volume of the cube is a cube. And a is equal to 4r by root 3. So therefore 4r by root 3 the whole square. Packing efficiency is volume occupied by the two spheres in the unit cell divided by total volume of the unit cell into 100. And that is 68%. So body-centered cubic close packing is less efficient than HCP or CCP. We have studied one more close packing, that is simple cubic close packing. And there are 8 spheres. Now these two spheres touch each other. Therefore the side of the unit cell A is equal to R. And the edge length of the cube is 8. Now A is equal to R. Therefore the volume of the cubic unit cell is a cube, that is 8R cube. The effective number of atoms in simple cube is only 1. So therefore volume occupied is 4 by 3 pi r cube. So packing efficiency will be volume of one atom by volume of the unit cell into 100. And that is only 52.4%. That is the least efficient close packing. Determination of formula of a compound. Now we know the two most efficient close packing are CCP and SCP. Both show 74% packing efficiency. And this generates two types of oids. These are the tetrahedral oids and the octahedral oids. The number of tetrahedral oid is twice the number of close packed particles, and that of octahedral is same as the number of close packed particles, that is effective number of close packed particles. In ionic solids, the bigger ions, usually anions, form close packed structure, and the smaller ions, usually cation, occupy the voids. If cations are small enough, they will occupy tetrahedral oids, and if larger, octahedral oids. In a close packed structure, all tetrahedral and octahedral oids are not occupied. If in a given compound, the ratio of the fraction of octahedral or tetrahedral oids that are occupied depends on the chemical formula of the compound. So we can find out the formula of a compound if we know how much of the tetrahedral and octahedral oids are occupied. Consider an example. Atoms of element B form SCP lattice, and those of the element A occupy 2/3 of tetrahedral oids. What is the formula of the compound formed by elements A and B? If effective number of atoms in the lattice is n, then the number of tetrahedral oids will be 2n. Therefore, the number of B atoms is equal to n. B forms the lattice. So, number of A atoms will be twice that is 2n. If the effective number of atoms in the lattice is n, then the number of tetrahedral oids will be 2n. Therefore, the number of B atoms will be n because B forms the lattice. Now, the tetrahedral oids will be 2n, and out of that only 2/3 is occupied. So, the number of A atoms will be 2n into 2 by 3, that is 4n by 3. So the ratio of A atoms to B atoms is 4n by 3 is to n, or 4 is to 3. So therefore the formula is A4B3. This table gives a comparative study of the characteristics of different types of close packing. That is, unit cell close packing, effective number of atoms, coordination number, packing efficiency, radius of the atom, and the distance between the centers of neighboring atoms. So for simple cubic close packing, SCC, effective number of atoms is 1. In that case, the coordination number is 6. Packing efficiency is only 52.4%. Radius of the atom is A by 2. Distance between two atoms will be the diameter, that is 2 into A by 2A. Body-centered close packing, that is 2. Coordination number is 8. Efficiency is 68%. Radius of the atom will be root 3A by 4. Now, face-centered cubic lattice or cubic close packing, effective number is 4. Coordination number 12. Packing efficiency is 74%. So the relation between radius and edge length is A by 2 root 2. In hexagonal close packed structure, effective number is 6. Coordination number is again 12. Efficiency also is same, 74%. And the radius is related to edge length as A by 2 root 2. In the case of ionic crystals, the radius ratio of cation to anion will help us to predict the structure of the crystal. It is summarized in the given table. So this is an ionic crystal, and usually the cation occupy the void. So this is radius of the anion. This is the diameter or 2 radii of the cation. RA, radius of anion, and RC, radius of the cation. Now we can calculate the radius ratio. The radius ratio is equal to radius of the cation by radius of the anion. That is RC by RA. This table gives the radius ratio and a probable structure. If this radius ratio RC by RA is between 0.155 and 0.225, the coordination number will be 3 and the structure will be plain triangular. An example is boron oxide. Then if it is between 0.225 and 0.414, the coordination number will be 4. And the probable structure is tetrahedral void of FCC array of anions occupied by cations. Examples are zinc sulfide, copper chloride, silver iodide, etc. If the ratio is between 0.414 and 0.732, the coordination number is 6 and the probable structure is octahedral void of FCC array of anions occupied by cation. Examples are sodium chloride, potassium chloride, magnesium oxide, etc. If the ratio is greater than 0.732, then the coordination number will be 8. In such case, the structure may be the cubic void of simple cubic array of anions occupied by cations. Example is cesium chloride, cesium bromide, cesium iodide, etc. Let us consider some of the relations by which we can calculate density, unit cell dimension, etc. The effective number of atoms in a unit cell is Z. Now mass of each atom is taken as small m. Mass of the unit cell will be effective number of the atoms in the unit cell into mass of one atom. Edge length of the unit cell is A. So we use this equation for cubic crystals. So therefore the volume of the unit cell will be A cube. Density of the unit cell is mass of the unit cell by volume of the unit cell. That is Z into m by A cube. Now m is equal to molar mass by Avogadro constant. Na is the Avogadro constant. Therefore density is equal to Z into m by Na by A cube, that is Zm by A cube Na. So density is equal to Zm by A cube Na, where Z is the effective number of atoms in the unit cell, m is the molar mass of the crystal, Na is the Avogadro constant. And from this we get the value of A as cube root of Zm by Na into D, where D is the density. Let us work out some multiple choice questions from solid state part 2. Structure of solids and packing efficiency. Copper metal crystallizes in the FCC lattice with the unit cell edge length of 361 picometer. The radius of copper atom is option 1 127 picometer, 181 picometer, 157 picometer, 108 picometer. Since it is a numerical question, we have to find out the radius by calculation. For FCC lattice, the radius of the atom and the edge length are related by the equation R is equal to A by 2 root 2. Now A is given, that is 361 picometer. So R is equal to 361 by 2 into root 2 1.414, that is 127.65 picometer. So the correct option will be option 1. Lithium forms body-centered cubic structure. The length of the side of its unit cell is 351 picometer. Atomic radius of lithium will be option 1 75 picometer, option 2 300, option 3 240, and option 4 152. In a body-centered cubic structure, the radius of the sphere is given by R is equal to root 3 A by 4. And here also the edge length is given. So R is equal to root 3 into 351 by 4, that is 152 picometer. So option 4 is correct. Then 3. The edge length of a face-centered cubic unit cell of an ionic substance is 550 picometer. If the radius of the cation is 96 picometer, the radius of the anion is option 1 250 picometer, 398 picometer, 618 picometer, 179 picometer. So this is an FCC lattice. In a FCC lattice of an ionic compound, usually the anion occupy corners and the center of faces. So we assume that the anions form FCC lattice. The cation may occupy the octahedral voids. So we can expect a sodium chloride type arrangement. Along the edge of the anion, the anion and cation touches each other. So we can draw a figure. So bigger circles are anions and smaller circle is cation. So this is the cation is at the middle of the edge. Therefore, edge length A is equal to 2R plus. So this is radius of the cation, 2 radii, and 2 radii are anion. So it is 2R plus 2R minus. Edge length A is equal to 550 picometer. So 550 is equal to 2 into R plus. R plus is given, that is 96 picometer, plus 2 into R minus. R minus is the radius of the anion. Therefore 2R minus is equal to 358. Or R minus is equal to 358 by 2, that is 179 picometer. Then the radius, from the radius ratio, R cation by anion is 0.536, and this is within the range of 0.414 to 0.732, that is for an FCC lattice. So the answer is 179 picometer. In a cubic close packed structure of oxide ions, cations A occupy 1/6 of tetrahedral voids and a cation B occupy 1/3 of the octahedral voids. The formula of the compound will be option 1 AB2O3, option 2 A2BO3, Option 3, AbO3. Option 4, A2BO3. The number of oxide ions in the unit cell, that is 1 by 8 into 8 plus half into 6. So this is a cubic closed packed structure of oxide ions. So oxide ion form the FCC lattice. So the corner plus center of the faces, that is 4. Number of A ions occupy 1/6 of the tetrahedral. The number of tetrahedral will be twice this one, that is 8, and 1/6 are occupied by A. So 8 into 1/6 is 4 by 3. So number of B ions is 4 into 1 by 3. That is, B ions occupy the octahedral. There will be 4 octahedral. 1/3 is occupied by B ions. So that also is 4 by 3. So the ratio of ions will be 4 by 3 is to 4 by 3 is to 4. That is 4 is to 4 is to 12, or 1 is to 1 is to 3. So therefore the formula will be AbO3. So option 3 is the correct answer. If in a crystal lattice of compound, each corner of a cube is enjoyed by sodium ion, each edge of the cube has oxygen, and center of the cube enjoyed by tungsten, the formula of the compound. Option 1, Na2WO4, NaWO3, Na3WO3, Na2WO3. So here the corner atoms are occupied by sodium. So therefore corner sodium atom is, there are 8 corners and each corner atom is shared by 8 unit cells. So 8 into 1 by 8 is equal to 1. Each edge of the cube has oxygen. So 12 edges are there. Each edge atom is shared by 4 unit cells. So the number of oxygen atoms will be 12 into 1 by 4 is equal to 3. Now the tungsten atom at the center. Hence the number of tungsten atoms will be 1. Therefore the formula of the compound should be NaWO3. So option 2 is the correct answer. The vacant space in a FCC unit cell will be 26%, 74%, 32%, 46%. The packing efficiency for FCC or CCP is 74%. So the vacant space will be 26%. The metal sodium and magnesium crystallizes in BCC and FCC type crystals respectively. Therefore, the number of atoms of sodium and magnesium present in the unit cell of their respective crystal is 1, 4 and 2, 9 and 14, 14 and 9, 2 and 4. Now the metal sodium and magnesium crystallizes in body BCC and FCC. The effective number of atoms in BCC is 2 and FCC is 4. So therefore the answer will be 2 and 4. The total volume of atoms present in a phase-centered cubic unit cell of a metal is dash. R is the atomic radius. That is 8 by 3 pi r cube, 8 pi r cube, 16 by 3 pi r cube, 4 by 3 pi r cube. The effective number of atoms in a phase-centered unit cell is 4. So the volume will be, volume of one atom is 4 by 3 pi r cube. So total volume will be 4 by 3 pi r cube into 4. That is 16 by 3 pi r cube. So option 3 is the correct answer. An ionic compound has unit cell constituting of A ions at the corners of a cube and B ions on the centers of the faces of the cube. The empirical formula of the compound will be AB A2B, A3B, or AB3. The ionic compound has unit cell constituting of A ions. So A ions occupy the corner. So the number of ions in the unit cell will be 1 by 8 into 8, that is 1. And the B ions on these centers are the face of the cube. So there are 6 faces. The number of B ions in the unit cell will be half into 6. An atom in the face will be shared by 2 unit cells. So therefore number of A atoms 1, B atoms 3. So the formula should be AB3. If L stands for edge length of a simple cubic, body-centered cubic and face-centered cubic systems, then the ratio of radii of the spheres in these systems will respectively be 1 half L root 3 by 2L is to root 3 by 2L. 2 1L is to root 3L is to root 2L. Option 3 and option 4. And we can easily arrive at this from the radius ratio. So for radius ratio is simple cubic unit cell, it is A by 2, body center it is root 4, FCC it is A by 2 root 2. So the correct option will be 3. The number of carbon atoms present per unit cell of diamond is 4, 8, 6 and 1. So in diamond is FCC lattice and a half alternate tetrahedral voids are occupied by carbon atoms. So therefore the total number of carbon atoms in the unit cell is 8. A solid has structure in which A atoms are located at the corners of the cubic lattice, B atoms at the centers of the edges and sodium atoms at the center of the cube. The formula of the compound is 1 NaB2, option 2 NaB3, Na2AB2, NaB4. So we can draw a picture of that. So A atoms at the corners, B atoms at the middle of the edges, and the sodium atom is at the center of the unit cell. So number of corner atoms A, that is 8 corners are there. Each corner is shared by 8 unit cell. So the contribution from A atoms will be 8 into 1 by 8 equal to 1. B atoms are at the edge center and each edge is shared by 4 unit cell. So the contribution from B atoms will be 12 into 1 by 4, 3. There are 12 edges and the sodium atom is within the unit cell. So the ratio sodium is to A is to B is 1 is to 1 is to 3. So the formula should be NaAb3. In a cubic closed packed structure, it is found that the lattice has oxide ions and a half of the octahedral voids are occupied by ions of W and 1/8 of the tetrahedral voids are occupied by ions of X. If the charge of X ion is plus 2, the charge on the W ions will be option 1 plus 3, option 2 plus 2 plus 4 and a plus 1. For the number of oxide ions is 4. Now half of the octahedral voids are occupied by W. Since it is cubic closed packed, the effective number of atoms is 4. So the number of octahedral voids will be 4. So the number of W ions will be 4 into half, that is 2. So there must be 8 tetrahedral voids and 1/8 of the tetrahedral voids are occupied by X. So the number of X ions will be 1 by 8 into 8 equals 1. Now the charge of the X ion is given as plus 2 and that of oxygen is minus 2. So the formula is XW2O4. So XW2O4 X is equal to plus 2 into 1 Then suppose we do not know the charge of W, that is x into 2, then minus 2 into 4 equal to 0. So x is equal to plus 3. So option 1 is the correct answer. The packing efficiency of two-dimensional square unit cell shown below is 1, 39.27, 68, 75.05, 78.54. And this is the square unit cell given. The edge length is L and it is a face-centered one. And this is the face diagonal. Along the face diagonal, the three atoms touch each other. And the face diagonal is root 2L. Now root 2L consists of 4 radii. 1, 2, 3 and 4. So L is equal to 4R by root 2 or 2 root 2R. Now area of the square is L square. That is 2 root 2R the whole square. Now we have to consider the effective number of circles in the square. So a circle in the corner is shared by 4 unit cells. So this unit cell gets only 1/4. And 4 such corners are there, 4 in 1 by 4. And this circle is totally within the unit cell. So the effective number of circles is 2. Area occupied by circle is pi r square into 2. So packing efficiency is occupied area by total area. That is 2 into pi r square by 2 root 2 r the whole square into 100. That is 78.5%. So the correct option is option 4. A compound MbXQ has cubic closed packing arrangement of X. Its unit cell structure is shown below. The empirical formula of the compound Mx, Mx2, M2X or M5X14. And M atoms are represented by the square. It occupies the center of the edges. X atoms are circles and it occupies the corners as well as the center of the faces. The number of X atoms in the unit cell is 1 by 8 into 8 plus the face centers half into 6 is equal to 4. Or X atoms form a face-centered cubic lattice. The number of M atoms in the unit cell is at the edge 1. So only it is only at 4 edge centers. So each edge, one edge is shared by 4 unit cell. So it is 1 by 4 into 4. And this one is within the unit cell. So the total number of M atoms will be 2. So the ratio of atoms is M is to X is 2 is to 4 or 1 is to 2. So therefore the formula is equal to Mx2. Option 2 is correct. The correct statement regarding orthorhombic crystal system is 1. A equals B equals C. Orthorhombic crystal system has 3 Bravais lattices. Alpha equal beta equal gamma. Calcium sulfate crystal is an example of orthorhombic system. And now let us consider the crystal systems. In orthorhombic, A not equal to B not equal to C. So first option is wrong. But alpha is equal to beta is equal to gamma. They are equal and equal to 90 degree. And orthorhombic has 4 Bravais lattices. And a calcium sulfate is not an example for orthorhombic, it is for tetragonal. Option 1 is wrong. Orthorhombic crystal has 3 Bravais lattices, it has 4, so it is wrong. And alpha equal beta is equal to gamma, that also equal to 90 degree. That is correct. Calcium sulfate crystal is not an example of orthorhombic system. So the correct option is option 3. Question 17. The atoms of element Y form hexagonal closed packing and atoms of X occupy 2/3 portion of the number of tetrahedral voids. The formula of the compound formed by X and Y is option 1 X2Y2, X2Y, X3Y4, X4Y3. the element Y form HCP structure. Let the effective number of atoms in HCP unit cell be n. Therefore, the number of tetrahedral voids will be double that, 2n. X occupies 2/3 of tetrahedral voids. So the number of X atoms will be 2n into 2 by 3, that is 4n by 3. And Y forms the hexagonal close packing. Therefore, number of Y will be n. So the ratio of X and Y atom will be 4n by 3 is to n, that is 4 is to 3. So the formula is x4 by 3. Option 4 is the correct answer. Question 18. If the unit cell of a mineral has cubic close packed array of oxygen atoms with m fraction of octahedral voids occupied by aluminum ions and n fraction of tetrahedral holes occupied by magnesium ions, m and n are respectively are 1, 1 by 2, 1 by 8, 1, 1 by 4, 3, 1 by 2, 1 by 2, 4, 1 by 4, 1 by 8. Since the mineral is CCP array of oxygen atoms, the effective number of O2 minus ions will be 4. So the total negative charges will be minus 8. This charge must be neutralized by suitable number of aluminum 3 plus and magnesium 2 plus ions. The number of octahedral voids will be 4 and the number of tetrahedral voids will be 8. Now, if we choose 2 aluminum 3 plus and 1 magnesium 2 plus, the total charge will be 8. That is 3 plus 3, 6 plus 2, 8. So therefore, a fraction of aluminum 3 plus is, that is m is equal to 2 by 4, or that is 1 by 2. That is 2 aluminum ions, and aluminum ions occupy octahedral holes. So 2 by 4, that is half. Therefore, the fraction of magnesium 2 plus ions and magnesium occupy tetrahedral voids, and there is only one magnesium. So n is equal to 1 by 8. So the ratio will be half 1 by 8. If A is the length of the side of a cube, the distance between the body-centered atom and one corner atom in the cube will be 2 by root 3a, 4 by root 3a, root 3 by 4a, root 3 by 2a. Take the example of a cube. If A is the length of the side of the cube, edge length, the distance between the body-centered atom and a corner atom. So body-centered atom will be lying on the body diagonal. So body diagonal is root 3 by a. Root 3. Body diagonal is root 3a. So this is the center, and the body-centered atom will be here. Now the corner atom will be this one. So they touches each other. This is one radius, this is another radius. So this distance is half of root 3 by a, that is root 3a by 2. So therefore the answer is 4. If same type of atoms are packed in hexagonal close packing and cubic close packing separately, then the density of HCP will be greater than CCP, density of HCP will be less than CCP, density of both will be the same, density of HCP and CCP depend upon the temperature of the system. Both HCP and CCP has the same packing efficiency of 74%. So therefore both will have the same density. Density of both will be the same. Question 21. A mixed oxide is cubic close packed whose unit cell is composed of oxide ions. 1/4 of the tetrahedral voids are occupied by divalent metal X and the octahedral voids are occupied by a monovalent metal Y. The formula of the oxide will be 1xyo2, 2x2yo2, 3x2y3o4, and 4xy2o4. Given that the mixed oxide is cubic close packed, therefore the lattice type is FCC. The effective number of atoms in FCC is 4. Therefore, the number of oxide ions will be 4. So, unit cell is composed of oxide ions. Hence, the number of tetrahedral oids is 8 and the number of octahedral oids is 4. X ions occupy 1/4 of the tetrahedral oids. So, the number of X ions in the unit cell will be 8 into 1 by 4 equal to 2. Y ions occupy all octahedral oids. And the octahedral oids are occupied by monovalent Y. So the number of ions will be 4. So the ratio is X is to Y is to oxygen, 2 is to 4 is to 4, or 1 is to 2 is to 2. Therefore the formula is XY2O2. Also the total charge should be 0. That is plus 2 into 1 plus 1 into 2 minus 2 into 2 is equal to 0. So the correct option is option 4. Question 22. Given below two statements. One is labeled as assertion and the other is labeled as reason. Assertion. In close packing of spheres, a tetrahedral oid is surrounded by 4 spheres, whereas an octahedral oid is surrounded by 6 spheres. Reason. A tetrahedral oid has tetrahedral shape, whereas an octahedral oid has an octahedral shape. In the light of above statements, choose the most appropriate answer from the following options. 1. If A is not correct, but R is correct. 2. If A and R are correct and R is the correct explanation of A. Option 3. If both A and R are correct and R is not the correct explanation of A. And option 4. If A is correct but R is not correct. The shape of a void is different. Tetrahedral void means when the centers of the surrounding spheres are joined, a tetrahedron results. And when the centers of the spheres of surrounding octahedral voids are connected, an octahedron results. So, assertion is correct. In close packing spheres, a tetrahedral void is surrounded by 4 spheres, whereas an octahedral void is surrounded by 6 spheres. And the reason is wrong. Tetrahedral void has a tetrahedral shape, whereas octahedral void has an octahedral shape. So option 4 is correct. Next one is a paragraph type question. Read the following paragraph and answer the questions given below. All real crystal structures are three-dimensional. By stacking two-dimensional hexagonal close-packed layers, we can construct three-dimensional structures. In one case, spheres of the second layer are placed in the triangular voids of the first layer. This generates tetrahedral voids. All the triangular voids of the first layer may not be covered by second layer. In some cases, triangular voids of the second layer may come above the triangular voids of the first layer. This generates octahedral voids. When third layer comes, spheres of the third layer may cover tetrahedral voids of the second layer, and the third layer spheres are exactly aligned to the first. This generates AB-AB pattern and is called a hexagonal close-packed structure. In another arrangement too, the third layer is placed above the second layer such that the spheres may cover the octahedral void of the second layer. Here the spheres of the third layer are not aligned with the first or second layer and forms a pattern ABC ABC. Such close-packed structures are called cubic close-packed structure. Question 1. The coordination number for HCP and CCP structures respectively are 4 and 8, 8 and 12, 12 and 8, 12 and 12. For both HCP and CCP close packing, the coordination number is 12. Select the incorrect statement from the following options. Both HCP and CCP structure originate from external close packed 2D layers. Stacking of external close packed 2D layers generate HCP structure only. In HCP structure, every third layer is a repetition of the first layer. CCP structure generate face-centered cubic lattice. So we have to select the incorrect statement. Both HCP and CCP structures originate from external close packed 2D layers, and that is a correct statement. Then stacking of external close packed 2D layers generate HCP structure only. That is wrong. It generates both HCP and CCP. So the wrong statement is this one. In HCP structure, every third layer is a repetition of the first layer, ABAB pattern. In CCP structure, the CCP structure generates face-centered cubic lattice. That also is correct. The effective number of atoms in unit cell of CCP structure is 6, 4, 2 and 8. So the effective number of CCP is same as face-centered cubic lattice. So it is 4. The packing efficiency of CCP structure is 68%, 74 and 26. And CCP and HCP are the most efficient close packing structures. In both, the efficiency is 74%. Then choose the correct statement. HCP structure generate a cubic lattice. In HCP arrangement, every fourth layer is a repetition of the first. The only most efficient close packing arrangement is CCP. In CCP arrangement, the third layer covers the octahedral voids of the second layer. HCP structure generate cubic lattice. That is wrong. HCP is not cubic. In HCP arrangement, every fourth layer is a repetition of the first. That also is not correct. In HCP, every third layer is a repetition of the first. The only most efficient close packing arrangement is CCP. Both HCP and CCP are equally efficient. In CCP arrangement, the third layer covers the octahedral voids of the second layer. That is correct.